Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 11.4, which has to deal with the comparison tests. There's going to be two different comparison tests that we talk about here, and both of them are going to be very similar to a small note that we had in the previous section for the bounded sum test. If you recall, the bounded sum test was used to kind of show that if you knew that a series was specifically bounded by some number, then you knew overall that that series was going to converge. What it converges to, we don't know. The problem lied in that we knew a specific value. We knew that it bounded by a specific number. This comparison test is going to be a little bit nicer. In this case, all we need to show is that the series we're working with is less than something that's convergent. What it converges to, we don't know. Or it's greater than something that diverges. If we know that, then we likewise know that the series I'm looking at is either convergent or divergent. That's going to be the comparison test in a nutshell. The main takeaway, the difference between that with the bounded sum test, is that if we're trying to show convergence, I don't need to know what it's bounded by. I just need to know that it's less than some other series that I already know converges. Whether I know what that series converges to or not is irrelevant. So that's the bounded sum test in a nutshell. Suppose you have two summations, or you have two series with non-negative terms. I think the book says positive, but they don't necessarily need to be positive. They could just be non-negative, so they could include 0. For every situation where a sub n is always less than or equal to b sub n, after some point n is greater than or equal to capital M, then that means the sum b is going to be convergent. That means the sum a is convergent. You can see with that comparison here that if b is convergent, then that means anything less than b is convergent. Or, likewise, if a sub n is divergent, that means anything greater than that is also divergent. This should sound a lot like what we did back in section 7.8 with integral comparisons, where we found one integral that was greater than something we knew divergence, then that means the integral itself diverges. We're going to do the same thing here, and we're also going to very often compare, like we did in integrals, we're going to compare to p-series rather often. We're going to compare and show things that are less than a p-series that converges or greater than the p-series that diverges. That'll be a very common comparison for us. One other note about these comparison tests, particularly compared to what you'll see in the textbook, is that the textbook outlines that it needs to be true for all values n of the series. So if the series goes from 1 to infinity, the book implies that you need to show that that series is less than a series that's also, or you have to show that it's less than a convergent series also from 1 to infinity. That's not necessarily true. We don't care about the finite case. As I say here, if you can confirm that the terms in a series is less than another convergent series from the 100th term and on, we don't care about the first 99 terms. If the first 99 terms are greater, who cares? That's a finite amount of values that will add up to a finite value itself. If we can show the infinite case is converging, that means the whole thing converges. So we don't necessarily need to care about up to some finite value. So that allows us a little bit more flexibility with this. We don't need to be pretty stringent on, oh, well, it's not true for the first 5 terms, so this doesn't work. If it's true for the 6th term and on, then we're good. That's all we need. Okay, let's do a couple examples of these. Now, because all we're doing is comparing, we don't actually need to do the sum. All we're really doing is looking at the fraction that we have here, or what the summation looks like, and then trying to show if this is greater than or less than something. Now we see n over 5n squared minus 4. If you ever see polynomials like this, your inkling should be to try to compare to an associated p-series. If I just look at the highest terms on top and bottom, I see n over n squared, which is 1 over n. That means I'm probably comparing to 1 over n. Now 1 over n, that p-series, otherwise known as the harmonic series, this diverges. So that gives me the hint that I should probably compare this in a divergent way, meaning I'm trying to show that this is greater than something that's divergent. And we'll see if that works out pretty nicely. if we take n over 5n squared minus 4, if we take out that 4, then that means this is going to be greater than n over 5n squared. Because if we take out 4, then that means this would have a larger denominator. Or rather, the result of that, 5n squared would be larger than 5n squared minus 4. So therefore, because the denominator is larger, it would likewise have a smaller value overall. And then we recognize that this is 1 over 5n, or 1/5 times 1 over n. I write it like that because that will allow us to make the comparison and say that this sum from 1 to infinity of n over 5n squared minus 4 is going to be greater than 1/5 times the sum from 1 to infinity of 1 over n. By the way, to be safe, you can also just say greater than or equal to. It doesn't exactly matter. However, we know that because the sum of 1 over n diverges by p-series, then we know our series will also diverge by the comparison test. Essentially, we show that we have a series that's bigger than something that goes to infinity. So if you have something that's bigger than something that goes to infinity, that means it just goes to infinity faster. So that's an example of showing divergence here. So divergence. Again, remember, like in the last section, you always want to make a statement about why it converges or diverges. You don't want to just leave it with this information and say that it's good. You also want to be able to analyze that, use the right comparison, and why. So we have that because this sum here, 1 to n, will diverge by the p-series. That means our other series will also diverge because it's larger. The reason I also brought that 1/5 out is because you could pull the 1/5 in front of the summation, and 1/5 times something that goes to infinity is still infinity, just slower. Let's do another one. We have here the sum from 1 to infinity of 1 plus cosine of n over e to the n. Now with trig functions, when you see trig functions like cosine or sine, you want to think about what they act like as n goes to infinity. We know that if we look at 1 plus cosine of n over e to the n, we know that cosine will always be between -1 and 1. And likewise on the denominator, to try to think about how I want to compare this, e to the n, that kind of looks like a geometric series, because that looks like I have a constant taken to a power. And that constant, e, is on the denominator, so that's 1 over e, which is less than 1. I'm probably trying to show that this is convergent. So I probably want to compare this to 1 over e to the n power, which is convergent by the geometric series, because 1 over e is less than 1. So that kind of gives me a hint of how I want to address this. Likewise, because I want to show that it's convergent, that means I want to take these values of n and show that this is less than something, or less than or equal to. And as we said, cosine goes between -1 at 1, so that means it's at most 1, so I should be able to say that this fraction is always going to be less than or equal to 1 plus 1 over e to the n, because cosine is itself at most 1. So then we see this as 2 over e to the n, or, to make it look like a geometric series, 2 times 1 over e to the n. Therefore, we have that the sum from 1 to infinity of 1 plus cosine of n over e to the n is less than or equal to, again, equal to because cosine could be 1 at some cases, the sum from 1 to infinity of 2 times 1 over e to the n. And again, we know that the sum of 2 times 1 over e to the n converges by geometric series, because 1 over e is less than 1. So by the comparison test, so does the sum of 1 plus cosine of n over e to the n. Note that the way that I wrote this actually looks a little bit different than the way that I wrote it earlier. I used like different wording. Last time I said that because the other one was divergent by P series, then our series will also diverge by the comparison test. And I took the second clause and rewrote that and said, so by the comparison test, so does this series or our series. There's no set way of writing it. You just always want to make sure that you identify what test you're using and why you know that the one you're comparing to converges or diverges. But that would be it. Note that in both these cases, we haven't been able to confirm what it converges to. Or in the previous case, we had divergence. We knew it diverges to infinity. But for this one, we don't know what value this sequence or series converges to. We're not going to be able to find that using this. We're just going to be able to find if it converges or diverges. We can bound it. We can bound it using this geometric series. We don't know what the series itself is going to converge to. All right, how about this one? K times sine squared k over 1 plus k to the third power. Looks complicated, but again, we have a trig function. We should think about what that trig function does. This is squared, so this is going to hop between 0 and 1. Technically, hard brackets, because it could equal 0 and 1 at multiple places. So then what we can say, kind of like with the last one, we look at the highest terms. We have k over k cubed. So we could think about that as k over k cubed is 1 over k squared. That converges by P series. So we likewise want to probably show a comparison here that shows a comparison that converges. Also, because these are k's, this should be a k for the summation. But so k sine squared of k over 1 plus k cubed. Let's make sure our comparison works. This is going to be strictly less than or equal to k times 1 over 1 plus k cubed, replacing sine squared with what it is at most. Likewise, this, because the denominator has a 1 plus, if we take out that 1 plus, that's also going to be strictly less than k over k cubed, because this one would have a larger denominator, so it would be likewise less than. And k over k cubed is 1 over k squared. So following this inequality, we can then say that our sum from 1 to infinity of k sine squared k over 1 plus k squared is going to be strictly less than, we know strictly less than because of this, the sum from 1 to infinity of 1 over k squared. So again, we make our statement. So the sum of 1 over k squared converges by P series. And we can say specifically that P, which is 2 in this case, the exponent is 2, which is greater than 1. So by the comparison test, the sum of k sine squared k over 1 plus k cubed also converges. And that would be that example. Hopefully you're starting to see a pattern of how I'm working with this. I'm looking at the series and trying to think about what direction I want to show with convergence or divergence. Because you can always show that something is greater than something else or less than something else. But you want to try to get an inkling of what comparison you want to shoot for. And then try to see if your logic can follow through with that. Then I show that summation to show like specifically what I found. And then I make my statement about whether it converges or diverges based on what I know so far about p-series and geometric series. Common ones we see. Let's do one more with the standard comparison test. Sometimes called the ordinary comparison test. We have n over 2 to the n times n plus 1. Alright, well, n over n plus 1 is akin to 1, more or less. But the rest of what we see, 1 over 2n, that's the same as 1/2 to the n power. That looks like a geometric series. And that converges by a geometric series because 1/2 is less than 1. So likewise, we're probably going to address this by thinking about comparing and showing that it converges. So I'm going to take n over 2 to the n times n plus 1 and try to show that this converges. First, I'll take out that 1 over 2 to the n power times n over n plus 1. I haven't changed anything, so I keep equality here. But I know this is going to be less than 1/2 to the n power of n over n. Because this one has a higher exponent. Well, yeah. This one has a higher denominator. So that means that it would likewise be less than something with a lower denominator. And n over n is the same thing as 1. So this is just 1/2 to the n power. So then we have that the sum from 1 to infinity of n over 2 to the n times n plus 1, we've shown that this is strictly less than, or less than or equal to even, less than or equal to the sum of 1/2 to the n power from 1 to infinity. Now if you note, this isn't a perfect geometric series, but we can make it one if that trips you up. It's supposed to be 1/2 to the n minus 1 power. And so if I want n minus 1, I just need to take one of those 1/2s out. So we have 1/2 times 1/2 to the n minus 1. But that still converges by geometric series. So we'll say that the sum from 1 to infinity of 1/2 times 1/2 to the n minus 1 converges by the geometric series. We know that because 1/2 is less than 1. So by the comparison test, so does the sum of n over 2 to the n times n plus 1. Again, always make that statement. All right. Now, you'll note that there are some problems with this. For example, if I even just took this problem, say if I look at what I had evaluated right here, what if instead of n over n plus 1, this was 1 over n minus 1? Well, then now I can't show the inequality I want to. Now I can't show that that is less than or equal to 1/2 to the n power times n over n, because it's not now. The one on the left-hand side here actually is greater than. However, it should be obvious that this fraction is still going to 1, more or less. So I need something else in order to still show this comparison that I should understand, I should already know. And that's what's going to lead us to what is called the limit comparison test. So basically, as I have here, probably the most important point, let me make sure I have a higher highlighter. these series tend to look like series you want to compare to a p-series or a geometric series, something that you want to do the correct comparison, but the terms don't work out nicely. Or there are too many terms in the polynomial that don't show the right comparison necessary. So maybe if I had a minus in a polynomial instead of a plus somewhere, and that let me not show either greater than or less than. So if they look like you want to do a comparison, but it doesn't just work out nice, try doing what we're going to call a limit comparison test. A limit comparison test is where you take your series a sub n. So that's the series you start with. And where you're going to compare to is a series b sub n with positive terms. We say positive because we're going to throw these over each other. We're going to take the limit of a sub n over b sub n. Note that this is not the summation of a sub n over the summation of b sub n. We just want to take the nth term of a over the nth term of b and evaluate what that limit equals. Do that in green. And we want to evaluate what that limit equals, which I call L. If that limit is between 0 and infinity, so it's not 0, it's not infinity, it's somewhere in between, it's a finite number, finite positive value, then that means a sub n and b sub n will converge and diverge together. So if, say, the one I compare to b sub n, if that one converges, then so does a sub n. If b sub n diverges, then so does a sub n. If it's the case, though, that L is equal to 0 and b sub n converges, then we also know a sub n converges. If a sub L equals 0 and b sub n diverges, though, we don't know what a sub n does. It could converge, it could diverge. We would say that this is inconclusive. So I have that here. Take note that if L is equal to 0 and b sub n diverges, then the test is inconclusive. And if the limit is infinite, the test is also inconclusive. So it doesn't help us if the limit is either 0 and b sub n diverges, or if the limit is infinity at all. In either of those cases, that would mean you need to do another test. The test that we have here didn't do the trick. Now, the main way to try to think about what we want to do with the limit comparison test is the same way that I was doing with the comparison test earlier. Note that every time I was trying to consider what I saw here, like n over n plus 1, 1 over 2 to the n, or in the previous case, I saw basically k over k cubed. That is what I want to think about when trying to think about what I compare to. If this didn't work out and I had 1 minus k cubed on the bottom or something, then, or negative 1 plus k cubed, and I still want to compare to 1 over k squared more or less, then I could do that with a limit comparison test using b sub n as 1 over k squared. So I still want to think about what I would have wanted to compare to, and that's going to be my summation I work with as b sub n. Okay, as an example here, we have the summation of n cubed minus 3n minus 12 over n to the fourth plus 5n. Now again, if we look at those leading terms, I see n cubed over n to the fourth. Wrong pen. There we go. N cubed over n to the fourth. That's the same as 1 over n. That's harmonic. We know that this diverges. However, I can't compare this nicely to a harmonic series. If I try to do n cubed minus 3n minus 12 over n to the fourth plus 5n, I cannot show that this is greater than something if I were to try to take out terms. For example, n cubed minus 3n minus 12, if I take out 5n and have n to the fourth, this is not true. 5n makes the denominator over here larger, which makes the overall value smaller. So that doesn't work. And also, if I kept 5n down here and I took out the top two terms, or even just one of them, this is also not true. Because the top has some subtractions on the bottom, which overall makes it smaller. So you see, I want to compare to 1 over n. I want to show that this is greater than something, but the values that I have don't really work out for me. That is why I'm going to try to use limit comparison test. So, going to use b sub n as the summation of 1 over n from 1 to infinity, which again diverges. We're going to need to know that. And now we're going to do a limit comparison test. So what we're going to do is find the limit as n approaches infinity of a sub n, which is what we have here, n cubed minus 3n minus 12 over n to the fourth plus 5n, over b sub n, which we have is 1 over n. So I have here a sub n over b sub n. This limit, as n approaches infinity, because I have a fraction over fraction, I can flip those and say this is n cubed minus 3n minus 12 over n to the fourth plus 5n times n over 1, multiplied by the reciprocal of the denominator. And that gives us the limit as n approaches infinity of n to the fourth minus 3n squared minus 12n over n to the fourth plus 5n. This limit we can do by just looking at the leading terms. Since the leading terms are the same, we know by the leading terms test for our limits that this limit should then approach the coefficients of them, which is 1 and 1 respectively. So this approaches 1 over 1 or just 1. So that's our limit so far. Now, be careful. A lot of people stop here and say, oh, we got a number, so that means it converges to that number. That is not true. We have a value, which is the value for this limit comparison, and it is between 0 and infinity. But that allows us to either show convergence or divergence. So since L equals 1 is between 0 and infinity, and the summation of b sub n is divergent. Remember, b sub n was this right here. That's the summation of b sub n. Then that means we know that the sum of 1 to infinity of n cubed minus 3n minus 12 over n to the fourth minus 5n is divergent. And we also want to say by the limit comparison test. So we showed here that it was divergent. Again, a lot of people have the problem that when they evaluate this limit and they get a finite number, they think that that means that it is converging to that number. That is not true. The limit comparison test is really just a marker. Whatever the value for the limit you get, as long as it's finite, then you can show either convergence or divergence. If it's equal to 0, you can only confirm convergence. So be careful with that. So a couple other examples. We have the sum of 3n minus 2 over n cubed minus 2n squared plus 11. Again, like the last one, we just want to look at the leading terms here. The leading terms are 3n over n cubed. So that's 3 over n squared. This we know converges. And that's what I'm also going to compare to. So I'm going to say that the summation of b sub n is the summation of 3 over n squared, which we know converges by p-series. So then I'm going to take the limit as n approaches infinity of a sub n, which is our original series, divided by b sub n, but like we did with the last time, we're really just going to multiply by the reciprocal. So 3n minus 2 over n cubed minus 2n squared plus 11 times the reciprocal of 3 over n, which is n squared over 3. That gives us the limits as n approaches infinity of 3n cubed minus 2n squared over n cubed minus 2n squared plus 11, or even 3 times all of those. And so what we have then is that this is going to 3n squared over 3n squared. This is again going to 1. And so yet again, we have a value of 1, but in this case we say that since the summation b sub n is convergent by p series, and I'll say L equals 1 satisfies 0 less than L less than infinity, then the summation from 1 to infinity of 3n minus 2 over n cubed minus 2n squared plus 11 is also convergent by a limit comparison test. Note that we had the same result in this one as we did in the last one. Both of these resulted in limits that evaluated to 1. But the overall result showed that one was divergent, the other one was convergent. The first example, or example 5 we did, showed that it was divergent. This one showed it was convergent. It all depends on what you were comparing to. Last time we were comparing to a divergent series. That's what led to a divergent evaluation. Here we compared to a convergent series, which led to a convergent evaluation. I also want to highlight yet again, I use different wording when evaluating this. I said since b sub n is convergent by p series and L equals 1 satisfies 0 less than L less than infinity. That's still saying more or less the same stuff as I did last time, where I said L equals 1 is between 0 and infinity and b sub n is divergent. It's still saying the same stuff, just in a different order. It doesn't necessarily matter. You have freedom in terms of how you want to word things, as long as you still bring up the same information. The main keys to note here, or that you need to make sure you point out whenever you do these. The summation of b sub n is convergent or divergent. You need to talk about that. You need to talk about the value of L that you got. And then your overall evaluation of convergent or divergent via the limit comparison test. Those need to be brought up. Okay, let's do a couple more. These ones are going to be a little bit tricky, particularly example 7. If you want to try this one on your own first, go for it, but you're going to find something kind of strange with it. Alright, with ln, or natural log of n over n squared, there's a couple different things you can try to work with. Maybe you can do this with an integral test, because we see natural log of n. You would probably have to do by parts. But we're going to try to do this with limit comparison test. Now, I'm not exactly sure how this is going to evaluate, so I'm going to do some testing. Maybe I want to compare this to 1 over n squared. So, limits as n approaches infinity of natural log of n over n squared. And if I'm comparing to b sub n is 1 over n squared, then I'm going to evaluate that as n squared over 1. That limit then cancels out those n squareds, and we have the limits as n approaches infinity of natural log of n, which goes to infinity. So that's inconclusive. Limit comparison test doesn't really work with that. Alright, well, maybe it's not convergent then. Maybe it's divergent. Let's maybe use b sub n equals 1 over n. See what that does. The limit as n approaches infinity of natural log of n over n squared times n over 1 will give us the limit as n approaches infinity of natural log of n over n. If you do L'Hopital's on this, you get the limit as n approaches infinity of 1 over n, which is 0. And this one is also inconclusive, specifically because b sub n is divergent. If we get a limit equal to 0, and the one we compared to was convergent, then we're fine. But if we got a limit equal to 0 and it's divergent, then it's not good. So far it's not working. Now, what we're actually going to try to do instead is the one in between these two. Let's try b sub n equals 1 over, instead of n to the second power or first power, let's try right in between 3/2 power, or 1 1/2. May seem odd, but this is a very kind of strange problem. Let's see what this one does. Again, it can take some creativity to figure these out. Natural log of n over n squared times n to the 3/2 over n. That will give you the limits as n approaches infinity of natural log of n over n to the 1/2. And if we do L'Hopital's on that, take the derivative of the top and the bottom. Natural log of n will give you 1 over n to the 1/2. The derivative of that one will give you 1 over n to the 1/2, or 1 over 2 n to the 1/2. So you actually get 1 over n times n to the 1/2 over 2. Yeah, because it would flip to the other side. So you get the limits as n approaches infinity of 1 over 2 times n to the 1/2. And that goes to 0. That's the same result we just had. However, we have that the limit equals 0 and b sub n converges by p series. Converges because the denominator is 3/2, or the exponent is 3/2. So by the limit comparison test, the sum of natural log of n over n squared converges. A little bit of a tricky one. Usually I'll say, in a lot of times when evaluating things like this and your situation comes out to be inconclusive with one test, usually the recommendation is try another test. Again, maybe the integral test would work here. I think it would still take more work than what I have here, because you would have to do by parts, looks like, to evaluate that natural log. So I'd recommend against using by parts with that, and instead just doing a couple of these, trying to figure out a good situation. If you get a couple inconclusives going in both directions, either for convergence or divergence, try testing something in between. Now, as a last example, we're going to determine if this series is convergent or divergent. We have n factorial over n to the n. That's going to be really, really weird. Now, we're not too familiar with that, so maybe let's try writing down some of these terms. Let's think about what the partial sum look like. If I have 1, I have 1 over 1 to the 1, so 1 over 1. If I have 2, I have 2 factorial, which is 2 over 2 to the second power, which is 4. 3 will give me 6 over 3 to the third power, which is 27. And I can keep going on in this fashion. 4 over 4 to the fourth power is 256. 4 factorial, sorry. 4 factorial is 24. 5 factorial is 120. Over 5 to the fifth power is 3125. 6 factorial gives you 720 over 46656, etc., etc. Not really seeing too big of a term, and the main issue here is that n factorial, because we don't really know how to work with that yet. In the next couple sections, we're actually going to have a way of dealing with this specific summation that's actually going to be very, very nice. But what we want to try to see is if there's a pattern with that numerator, if there's something that I can change that into, or if I can compare that by, to hopefully show if this is convergent or divergent. Based on what I'm seeing, I see the denominator is getting way larger a lot faster, which makes sense. N factorial is just going to multiply the numbers from 1 to up to n, whereas n to the n is going to multiply n times n times n an equal number of times. So it makes sense that the bottom is getting way bigger. This looks like it should be convergent. But we need to try to figure out something to do for that top. And the easiest thing that we can try to compare to show something is convergent is 1 over n squared, right? 1 over n squared from the p series is a very nice convergence. But we have n to the n power on the bottom. Well, what if we try to look at n factorial as some exponent of n? We recognize these values of n factorial, and if we want to reduce this down to 1 over n squared, let's try to compare n factorial to n to the n minus 2. That way, if I divide those by n to the n, I get overall n over n minus 2 becomes 1 over n squared. Now, what I want to show is that this is less than that, and that would show it's convergent. And n factorial and n to the n minus 2, not necessarily true for all cases. Let's test. If I have n factorial and n to the n minus 2, let's plug in numbers and see if this is true. So plug in values for n. I'll say 1, 2, 3, 4, 5, 6. We already know these ones. For n factorial gives you 1, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. How about n to the n minus 2? So that's 1 to the 1 minus 2, so 1 to the negative 1 power is still 1. Okay, so far it's equal to. How about 2? 2 to the 0 power is 1. Uh-oh, that's not good. We want to show that these values are greater. 3 to the 3 minus 2 is 3. 4 to the 4 minus 2 is 4 squared is 16. It's starting to get bigger. 5 to the 5 minus 2 is 5 cubed. And 5 cubed is 125. Oh, starting to get bigger. And 6 to the 6 minus 2 is 6 to the 4th power, which is 1296. And when we see this trend continue, that n to the n minus 2 is going to be larger after this point. So then what we can say is that this summation from 1 to infinity for n factorial over n to the n is going to be less than or equal to, actually strictly less than, the summation of 1 over n squared, specifically for n being greater than or equal to 5. If n is greater than or equal to 5, then we show that this is true. Should be n to the n over here, actually. Yeah. So for n is greater than or equal to 5, this is true, as we showed here. All right, then that means this is actually a comparison test. Then, by the comparison test, since the summation of 1 over n squared is convergent, and that's a p-series, then the summation of n factorial over n to the n is also convergent. So that's actually a comparison test. Alright, so that one's a little bit more creative to try to figure that out. And that's just because n factorial is hard to work with at the moment. But moving on, it will be easier and easier to work with. There are actually ways to apply and change n factorial into some actual exponent, really, and compare those adequately. Overall, that's it, though, for section 11.4 here for comparison tests. If you have any questions, feel free to put those in the comments below, or ask your instructor directly. With that said, I hope you have a nice day.